Thank you. We're already live on YouTube, and so I would just like to have a quick announcement before we start. So as we discussed briefly in the first lecture, so Shayan is proposing that we start a reading group, an international reading group, to sort of give some posterity to this course, that we can keep the momentum going and study some relevant papers and so on. So we'll be sending an email today with further instructions on that, and then anyone that's interested in participating, that would be fantastic. Okay, so other than that, Nicole, good morning, thank you again. You have the stage.
Thanks very much. Welcome back. What we're going to be up to today is here on the screen. Hopefully all of you can see it. We'll start with a quick review of the last lecture, then start on a whirlwind tour of the various subfields of quantum thermodynamics, of which there are quite a lot. Then we'll talk about a few of them in some detail, starting with quantum thermal machines, and then, if time permits, we'll get to quantum clocks. No pun intended. First, what did we do during the last lecture? We saw the homework problem, which turned out to be the Brownian ratchet, or Feynman-Smoluchowski ratchets. We talked again about Szilard's engine and saw a number of variations on it. Landau erasure results from reversing Szilard's engine. Landau erasure has been used to propose a resolution to Maxwell's Demon paradox. Then we talked about quantum effects on Szilard's engine and Landau erasure. We said that in the quantum regime, inserting the partition in the middle of the box can cost work. If you have multiple particles in the box, then they obey particle number statistics, which can depend on which type of quantum or distinguishable particle you have. And there can be entanglement between the system of interest and a memory accessible to the agent. Then we talked about possible definitions for quantum work and heat. First, we talked about why we even need to think about how to define work and heat in quantum thermodynamics, and we looked at a few sample definitions. But today, I'd like to start on what I'm calling a whirlwind tour of the subfields of quantum thermodynamics. I like to think of quantum thermodynamics as a landscape on a map that has a bunch of city-states. Different communities in quantum thermodynamics have different perspectives on quantum thermodynamics. They use different toolkits. And so I think of each of those subfields of quantum thermodynamics as one of these city-states. There's some interaction between the city-states, but it's worth looking at these different sort of cultures on their own footing. So we'll take a brief tour of the map. It will be a whirlwind tour, like those tours of London and Paris and Rome and Venice in 1 week. Those are never satisfying, so this isn't going to be fully satisfying, but it's going to convey at least a taste of each of several subfields. So you can identify the subfields that interest you and then explore those further after the mini course. This is the list that at least I've come up with of the city-states. One is the city-state of quantum thermal machines. Here we ask, for example, what if a quantum engine powered your car? There are also autonomous quantum clocks, which arguably belong in category 1, but I'm going to discuss them separately. So suppose that you want to build a quantum drone that delivers packages from quantum Amazon. This drone needs to be an autonomous quantum machine that can operate independently. So it needs some internal mechanism that tells it what to do when. So it needs an internal, i.e. autonomous clock. Since the whole machine is quantum, also the clock has to be quantum. There's the city-state of fluctuation relations, which is at least very closely related with stochastic thermodynamics. Suppose that systems of interest are small and far from equilibrium, then those undergo processes and certain quantities characterize those processes like heat and work. And those quantities fluctuate from trial to trial, far from equilibrium. So we ask, what can we say about those quantities' statistics? Relatedly, we have the subfield of one-shot statistical mechanics. Conventional thermodynamics concerns the thermodynamic limits, which involves infinitely many particles, an infinite volume, and self-averaging of the particles. So what if we're interested in small systems and rather than averages, what you're guaranteed to be able to achieve in a single shot? So here we tend to use entropies other than the Shannon entropy, the von Neumann entropy, and the conditional entropy that we already saw. A category near and dear to my heart consists of applications of quantum thermodynamics across science. We, as quantum thermodynamicists, now have a pretty well-defined toolkit of quantum thermodynamics. So we can take that toolkit and use it as a new lens through which to view chemistry and condensed matter and atomic molecular and optical physics and high energy and biophysics. Another city-state consists of non-Markovianity, or finite-sized baths, or relatedly finite-sized baths. Matteo will mention this topic. Conventional thermodynamic baths are infinitely large and have very, very, very short memories. Real-world baths have finite sizes and they do retain information about the system that they received from the system of interest that can then act back on the system of interest. So how do these properties change our expectations? I believe that Matteo will also talk about algorithmic cooling. Suppose that you want to run a quantum computer. So you need a bunch of ancilla qubits prepared in some simple fiducial state like the 0 state. So we can regard these 0 qubits sort of as baths at 0 temperature. Yesterday we talked about how we can assign to a spin an effective temperature. That's the idea here. So we can cool these qubits to this valuable 0 state by manipulating the correlations between the qubits. Matteo will also discuss this topic. So contextuality is in a sense the property that at least some entanglement has that enables entanglement to power superclassical computation. So it is something that really divides classical physics from non-classical physics. And this shows up in some quantum thermodynamic protocols as, and you can, if you detect it, then you can verify that this protocol really is non-classical. Thermodynamic uncertainty relations are a quite new topic. They belong to some extent within stochastic thermodynamics. Despite the name uncertainty relations, quantum and classical versions of these have been proved. Suppose that you have some small non-equilibrium system interacting with big baths. Particles and heat and so on hop around. So they might form a current that changes in time. And this current's relative variance can be bounded with the entropy that's dissipated in the baths. Finally, we reach the city-state of resource theories for thermodynamics. I'll talk about this a few lectures down the road, and also Matteo will talk about it. These are simple information theoretic models for thermodynamic settings. They overlap with one-shot statistical mechanics. Oh, we won't have time to visit all of these city-states, but again, this course is intended to show a glimpse of what's out there so that you can figure out what interests you and explore on your own. I saw a little bit of activity in the chat, so let's see what's going on there. Okay, looks like just some comments about turning off cameras. Then let's start on quantum thermal machines. These are used to, or rather, let me say, these use heat and work, or produce heat and work, or store heat and work. Examples include engines, refrigerators, the closely related heat pumps, ratchets, such as the last homework problem, and batteries. Also, again, arguably clocks, but we'll talk about those separately. Today's thermal machines are largely classical. We can ask, what if we built quantum thermal machines? Or what if we built thermal machines from quantum components? I'll provide a few examples. This is a list of samples, a starting point, so it's not going to be exhaustive. I want to talk in some detail about the first quantum heat engine that was proposed. So two of the following authors recognized that a certain quantum system can be seen as an engine in 1959, but I'm going to focus on their 1967 follow-up paper together with another author. The setup is as follows. We have, as our heat engine, a maser. So a maser is like a laser, except instead of spitting out optical light that we can see, it spits out microwave radiation. It consists of a collection of N three-level atoms in a cavity. So here's our cavity. We have a bunch of atoms. Each atom has levels 1, 2, and 3. Let's denote by N sub j the population of level j. That is, if you measure all of the atoms in the cavity, you measure each atom's energy, then you will find that some number of those atoms output the answer j, and that is N sub j. Alternatively, if you're looking at one atom you measure its energy, then n sub j is the probability that you'll obtain outcome j. Radiation, more light, or in a certain case, fermions, serve as the baths and the battery, which will store the work that is outputted by this engine. Our engine is going to interact with 3 baths, which are really equivalent, we'll see, to 2 heat baths plus 1 work storage system. Here again are our 3 atom levels. This transition exchanges heat with a hot bath. So this over here is some hot reservoir at a temperature T sub H. This transition interacts with a reservoir at a much lower temperature. Then levels 1 and 3 are connected by a heat bath at temperature infinity. I'll call this T sub W because the bath all the way on the right is the one that's really equivalent to a work reservoir. And we can see why for the following reason. So, heat exchanged with a T equals infinity bath is equivalent to work. We can convince ourselves of that statement in 2 ways. First, suppose that the bath receives a little amount of heat. dq. It will have a corresponding change in entropy given by ds equals dq over t. But if t equals infinity, then the entropy change is 0. So there is no entropy change associated with this transfer of energy. So it doesn't make the most sense to think about that energy transferred as heat. Second, suppose that this heat bath serves as a hot bath in an ordinary Carnot engine. The engine's efficiency equals 1 minus the low temperature over the high temperature. If this equals infinity, then the efficiency is perfect. So all of the energy that enters the engine from the hot bath is converted perfectly into work. So we might as well just think of that energy that comes from the T equals infinity bath as work. Consider the gap between some energies E sub j and E sub k. If the atom's JK gap comes to thermal equilibrium with the corresponding bath, then the ratio of the 2 populations satisfies this relation. They're related by an exponential. We call this condition detailed balance. It shows up all across statistical mechanics and thermodynamics. If the temperature is positive, as it usually is, and E sub k is greater than E sub j, then this exponent is going to be negative. So the kth energy level has a lower population than the jth energy level. So in summary, the high energy level is less populated. What if the temperature is negative? A negative temperature will invert the populations. Switch them so that the top level has a greater population. For example, let's consider the third energy level, the top energy level. In equilibrium, it has this Boltzmann population. If T sub h is just a little bit below 0, then the exponent is going to be positive. Since T has a very small magnitude, this E3 over kBt is going to have a very large magnitude. So N3 is going to be large. So now it's the upper level that has a large amount of population. If the energy is smaller, if we replace E3 with E1, then the population is going to be lower. That's what we mean by population inversion. So in this sense, a negative temperature bath is hotter than a T equals infinity bath. Because if the temperature equals infinity, then two levels will have equal populations. Whereas we just said, in this case, the more energetic level has a greater population. Okay, let's take a 1-minute break and review in our mind's eyes what we just saw and heard. Does anybody have questions about what we just covered? There are questions about what we mean by negative temperature. Just what I explained. So T is less than 0, and it leads to this population inversion. Negative temperature is a physical possibility, and we'll see that in the very next section. For example, quantum systems can have negative temperatures. So it looks like there's a little more activity on the chats. How do we derive the detailed balance equation? That lies outside the purview of this class because it's a bit more involved. This is something that Einstein talked about, and you can find it in, for example, quantum optics textbooks. It's But since the result itself, detailed balance, comes up so very often across thermodynamics, and it's useful, for example, to this problem, I figured it was useful at least to show the result. Can we really achieve Carnot efficiency with finite power? I'll talk about that actually later. And we are going to talk about a system that, according to the authors, functions as a Carnot engine. But we're going to just examine it as face value, put together the components, put together the process, and analyze how it works that way. Infinite temperature is a physical possibility because you can have a system that is that has all of its levels equally populated. Now, in practice, there might be a little bit of an approximation because nothing that we do in the lab is perfect, but it's physically possible. Okay, why can quantum systems have negative temperatures? So this reason is often taught in undergraduate statistical mechanics classes. So the following is intended to be a brief review. If you haven't seen this argument before for some reason and you get lost in the details, don't worry about the details. Just take away the main idea that quantum systems can have negative temperatures because they're discrete and finite. Their state space is finite. So if you want to see all the details, check a few standard textbooks or online lecture notes, or even online physics fora. The explanation is in a number of venues. But this is somewhat self-contained. Basically, mostly all that needs to be worked out is the steps in algebraic steps or calculus steps between different lines that I'll write out. Let's temporarily ignore level 1 because it can't couple to the T sub W bath, and that's what is going to have negative temperature to us, and we want to understand negative temperature. So when the atoms are in thermal equilibrium with a bath, each atom is in, oh, sorry, let's see. I want to ignore level 2 because that does not couple to the negative temperature bath. So each of the atoms is in one of 2 possible states, level 1 or level 3. So each of the atoms acts as a classical 2-level system. At thermal equilibrium, we can represent the state of each of these atoms with a matrix that is diagonal relative to the energy eigenbasis. So we can just focus on those diagonal elements, which form a classical probability distribution. So at the moment, we'll model the system with classical 2-level systems. The fundamental relation of statistical mechanics is a relation for a small change in the energy. We want to solve for the temperature. The temperature is the partial derivative of the energy with respect to the entropy at a constant volume and other extensive variables that are implicit in this ... and depend on exactly what system we have in mind. Let's flip this over. It equals the derivative of the entropy with respect to the energy at constant volume and so on, inverse. Consider all of the microstates accessible to this n-atom system. In one microstate, half the atoms, this particular half of the atoms point upward and that half points downward. In another microstate, none of the atoms point upward. And by point upward, I implicitly mean are in their top states rather than bottom states, and so on and so forth. If all of the microstates happen to occur with equal probabilities, then, according to our first lecture, the entropy equals Boltzmann's constant times the log of the number of microstates. This is just a reminder about the formula for entropy in one particular state that particular case that we've already seen. Again, N3 equals the number of atoms in their top levels. suppose that we fix N3, the number of atoms in the top level, then the number of whole system microstates given the fixed number of atoms in the upper level is the number of ways you can choose N3 atoms from big N atoms. Let's call that W of N3. Let me change notation. We've been using W to denote the work today, so I'll change this big W to omega. And I also used a curly W as the subscript of the temperature of the bath with a negative temperature. So let's use big omega here. That's, if I can write. For some reason I can't. That looks better. Okay, that's big N, choose little n sub 3. We know the formula for that. Suppose in a particular example that the number of atoms is very large and the number of excited atoms is close to 1/2 the total number of atoms. Then we can approximate this binomial distribution using Stirling's approximation. And this is something often done in statistical mechanics classes, so I'll leave out the details here. But it leads to this formula for the total number of microstates accessible to the n atom system, given that little n3 of the atoms are in their top levels. We just have 2 to the big N times a Gaussian distribution. This is a function of the number of atoms in their top levels. Sigma squared is the standard, the variance. That wasn't supposed to happen. Here we go. Also, that wasn't supposed to happen. The variance equals the total number of atoms over 4. This is just something that we can solve for. We can do a calculation to show this. But let's plot our function. On the x-axis, we'll have the total number of particles in their upper levels. On the y-axis, we'll have the total number of microstates accessible to the global system if n3 of the atoms are in their upper levels. This function is a Gaussian centered at big N over 2. We can take this expression for the total number of microstates and recall that that keeps happening. The entropy is Boltzmann's constant times the log of the total number of microstates accessible. And substitute in. We have Boltzmann's constant times the big N out front, also a log 2. And then because of what's inside the exponential, we have N3 minus big N over 2, all over twice the variance, minus this other term that comes from the normalization factor out front. Let's express this entropy in terms of the total energy of the system. Which I'll call E. The total energy is the energy of the top level times the number of atoms in the top level, plus the energy of the bottom level times the number of atoms in the bottom level. This N1 equals the total number of atoms minus the number in the top level. We substitute in, we rearrange. This equals E3 minus E1 times N3 plus big N times E1. Now we can solve for N3. N3 equals E minus the total number of atoms times E1 over E3 minus E1. We substitute into the expression for the entropy. And then we substitute into our expression for the temperature. We said earlier that the temperature equals the partial derivative of the entropy with respect to the energy at constant volume and so on, inverted. So let's substitute from N3 into S and then take this derivative. It's going to be relatively simple because N3 appears in this formula in only one place. Unfortunately, I don't think I will be able to show all the relevant expressions on the board at the same time because it's a bit narrow, but I'll work out the steps anyway. We take the derivative of the entropy with respect to the energy, so mostly everything remains the same except for this 1 and 3 part, which turns into an energy with respect to which we differentiate. We have negative Boltzmann's constant times the total number of particles times log 2 over twice the variance times 2. So these 2's will cancel. We have E minus N times E1 over E3 minus E1 minus big N over 2. And then we took a derivative. This needs to be inverted. We simplify. We find the negative of Boltzmann's constant times the total number of particles times log 2 over the variance times E3 minus E1 times 2. And we can substitute back in for this. That's just N3. Minus the total number of particles over 2. And again, we have our inverse. The part here is the most important part. If the number of particles in the top level is less than half the total number of particles, then the temperature is positive, according to our formula. And that's the usual situation. The temperature is positive, and according to the Boltzmann weights that we just looked at, most of the population is in the bottom level. But if N3 is greater than N over 2, so if over half the particles are in their upper levels, then the temperature is negative. So this is when most atoms are excited. But in summary, the reason why quantum systems can have negative temperatures is quantum systems are discrete and have finite state spaces. So that the entropy reaches this peak when half the particles are in the upper level and half are in the bottom level. Okay, are there questions about that very quick review? Why are we ignoring the second energy level? It's because we want to understand the concept of negative temperature. And in our engine setup, there's only one bath with negative temperature. You know what? I was right the first time. The negative temperature bath is connecting levels 2 and 3. So we want to ignore actually level 1. So that's going to be, that's a typo that should be propagated through the nodes. Suppose that we can measure its temperature. What's the result? Minus, yes, the temperature is, the effective temperature is negative. If N3, so the number of atoms in the top level, equals N over 2, so half the population is in its upper level, then the temperature will become infinite. Yes, it will, exactly, which is what we said earlier. We're focusing here on, well, I said earlier, the second level and the third level, but that was a typo. We should be focusing on I said earlier that we should focus on levels 1 and level 3. That was an error. We should be focusing on levels 2 and 3 because we have these 3 levels and the negative temperature bath connects these 2. How is a negative temperature bath created? Some quantum optics folks did a good job a few decades ago of coming up with ways of creating population inversions. I'm not going to get into the details of that since this isn't a quantum optics course, but I recommend checking out some quantum optics textbooks or lecture notes. What will be at the distribution at t equals 0? All the atoms will be in their lower levels. Okay, we will show that a negative temperature can give our heat engine an efficiency greater than 1, which means that the energy outputs more work than it absorbs as heat, which sounds strange, but we'll see how it works. Looks like there's a lot of activity on the chat. Let me take a brief look. There's a suggestion of a paper on creating negative temperature, a set of negative temperature cold atoms. Thanks for the reference. Okay, action, what happens with our engine? Again, we have a bunch of instances of this atom with levels 1, 2, and 3. The atom begins with whatever weights on its levels. That doesn't matter too much. The cold bath, which acts on levels 2 and 1, drops population from level 2 to level 1. Meanwhile, the hot bath, since it has a negative temperature, is going to lift probability weights from level 2 to level 3 because it creates a population inversion. Suppose that the hot bath has a negative temperature that's quite close to 0, which, according to our earlier argument, is actually really, really, really hot because it puts a lot of population on the top level. And suppose that the cold bath is somewhat cold, but not infinitely cold. It's not at 0 temperature. Then this cold bath will move some population down to level 1, but it'll leave some population on level 2. And the hot bath will move all that population up to level 3. Level 2 has practically no population. So this atom is hotter than the T equals infinity reservoir, because the T equals infinity reservoir wants to, as we just observed, split the populations evenly between 1 and 3. So it was very useful that people were asking a lot of questions about infinite temperature. Now we let the engine equilibrate with the T equals infinity bath. The atom has more population on the upper level than it will end up with after it equilibrates with a T equals infinity bath, because then it'll have even populations on the top and bottom levels. So some population drops down to the first level. As the population drops downward, that atom emits energy into the T equals infinity reservoir. So the atom emits energy into the infinite temperature reservoir, which we said is equivalent to work. What is the efficiency of such an engine? The efficiency, in general, of an engine is defined as the net work outputted over the heat absorbed during the stroke, in which the engine absorbs a net positive amount of heat. So the hot bath raises the atom across only one gap. Meanwhile, the T sub infinity reservoir receives energy from the atoms dropping across 2 gaps. So the efficiency is greater than 1 because W is greater than Q sub H. The interpretation of this efficiency is the engine outputs more work than it absorbs heat from the hot bath. Now, how quantum is this engine? In the very literal sense of the definition of quantum, so meaning a discrete packet, it is quantum. So the energy levels are quantized. But there are also classical systems that have discrete state spaces. Those classical systems can't support entanglement, but this engine doesn't rely on entanglement. Or even any other coherence that could be attributed even to a classical wave. So yes, this engine is quantum, but only to some extent. Questions about this engine? Soham Paul has raised a hand. Soham, can you, if you haven't written your question into the chat, can you go ahead and write it into the chat? One question is, where does the extra energy come from? It comes from the cold bath. Well, the cold bath, so the engine interacts with both the hot bath and the cold bath. The cold bath puts population on the bottom level. The hot bath puts population on the top level. And so it's more that the total, let's see, so we have energy moving downward during this interaction with the work reservoir. And that comes from partially that the engine, well, it comes from two sources. One is, we said that the engine could have, whatever initial state, it doesn't really matter. So it might have started off with a little bit of population on level 2. And also, if the cold bath isn't 100% cold, it isn't at T equals 0, then because of the way that Gibbs weights work, as long as the cold bath has some finite temperature, it'll put a little bit of population on level 2, and that will be bumped upward by the hot bath to level 3. When the atom equilibrates with T sub W, are the other baths detached? At least that is one way to run the protocol. Okay, let's take another moment to rest our eyes, not stare at the screen for too long. Okay, let's see, there are some requests on the chat. Let me start trying to sort these out. Okay, I'll try to move my cursor away from where I think it will be able to show up on your screens. I'm not entirely sure how that works because I don't actually have a cursor in my iPad, but I have a hypothesis, so we'll see if it works.
So I guess if you just try to move it to the left, like for now, yeah, that's perfect. Okay, it's not gone for us.
Okay. There are a lot of questions, and we should cover a couple more sections in this lecture, so I'll take one more. When we calculated the negative T, we considered equal probabilities for all microstates with energy between E and E plus dE. By having the system be in contact with a thermal bath, wouldn't we violate this assumption? We were trying to show where negative temperature comes from. Temperature is expressed in terms of the derivative of the entropy with respect to the energy. So we had to calculate the entropy, and the entropy comes from the probability distribution over the possible microstates accessible to the system if some number n3, which will vary across our graph of entropy, have some number n3 of the atoms are in their upper levels. And if we have a system like this, so we have a number of atoms that's such that there's not really any difference between them, they all experience basically the same thing, which is a very common assumption when we have some large ensemble of atoms and we don't have to think very much about any edge cases, then we can assume that they're all basically the same. So whether energy is in this atom so that it's in its top level, or instead in that atom so that it's in its top level, doesn't really matter. The two cases have equal probabilities. And we talked about the first quantum heat engine proposed. A lot more has been done on quantum engines since then. What are a few other things that we can do with quantum engines? First, we can boost the engine's power using coherences relative to the energy eigenbasis. This was shown in 2015. Someone asked about achieving Carnot efficiency at finite power. So, this was a paper that showed that you can imagine a quantum many-body system that can access two phases, such that there's a very particular sort of phase transition between them, such that if the strokes of the engine drive the engine across the phase transition, then in the limit, I believe the thermodynamic limits, as the engine grows infinitely large, the engine can achieve the Carnot efficiency at finite power. Usually that's impossible. To achieve the Carnot efficiency, you have to run the engine quasi-statically, infinitely slowly. If it runs infinitely slowly, then the energy that it outputs per unit time is zero. So there's this trade-off between efficiency and power. But in this limits, if you have this special sort of phase transition, then you can have both at once. You can also use a different phase transition of a quantum many-body system to make an engine that can be about as small or large as you want. It basically retains its properties, even though the nature of matter sort of changes as you scale from the nanoscale to the thermodynamic limits. And also, there are relatively few fluctuations in the work statistics of this engine. There are also many, many other things you can do with quantum engines. Lots of papers have been written. Also, many reviews have been written. I'll list a few and you can pick your favorite. This first one was written by Ronnie Kosloff, who is something of a king of quantum engines, and Amikam Levy. This is a bit older, it's from 2013. This is about multiple types of quantum thermal machines. It's pretty recent. This is also quite recent, very recent, more recent. It's about many-body engines, many-body quantum engines in particular. And also this is pretty recent. I'll mention one other type of quantum thermal machine in a little bit of detail. This is a battery. The field of quantum batteries has boomed recently because of this paper. These authors showed that if you have qubit batteries and you charge them in finite time, then if you use entangling operations, the entanglingness can boost the average power per qubit. Okay, let's move on to quantum clocks. I think we're at item number 4. In particular, autonomous quantum clocks. Ones that operate on their own without external control. So, first of all, what are these not? So what they aren't is the quantum clocks used today, for instance, in GPS, that are our most precise clocks. For example, I think the most precise quantum clock in the world is at Gila in Boulder, Colorado. So these involve atoms that absorbs energy from lasers, and then the results of feeding energy into the atoms is used to tune the lasers in a feedback loop. So such a clock is manipulated externally by classical control apparatus, such as these lasers. So this sort of clock is not autonomous. it's of a different sort. Now, why are we talking about clocks in quantum thermodynamics? First of all, clocks measure time, which is conjugate to energy. We said that thermodynamics is the physics of energy. Also, clocks need to run only forward to keep time accurately. So they break the time reversal symmetry in the fundamental laws of physics. The second law of thermodynamics should clue us into the idea that a clock can do this just if it dissipates and raises entropy. That is certainly in the purview of thermodynamics. Why should we study quantum clocks? In particular, autonomous quantum clocks. We might want to build autonomous quantum machines. For instance, we might want to build quantum computers that can operate on their own, or quantum robots that operate independently of external classical control. One of these quantum machines will need to carry its own clock, which will tell the machine what to do when. For instance, if we have a quantum computer, then the clock will tell the computer which logic gate to apply when. These machines, being autonomous quantum machines, need autonomous quantum clocks inside of them. Another motivation, which probably motivates most of the people in this field, is foundational. But we have to face the fact that in quantum theory, time is a parameter, though position isn't. It's an operator. There's an asymmetry that perhaps should bother us if we're used to more symmetric theories. So what do we do about it? Here are a few of the key ideas in the field. Not necessarily all of them, but a few ideas that will get our feet wet. First, there's a trade-off between work extraction and timekeeping. At least on the whole. There can be a couple of exceptions, but this is of a typical sort of statement. So say that you have one quantum system. If you want to extract work reliably, then having an energy eigenstate is useful. You can predict how much energy the system has, and so how much work the system can perform. Now, if instead you want for the system to keep time as a clock, then we might expect, analogously, apparently I can't write again. There we go. We might expect to want some sort of time eigenstate, whatever exactly that would mean, but just by analogy. time is conjugate to energy, so we might expect to want the system in an eigenstate of some observable that's conjugate to the Hamiltonian. Which means that the system would be in a very non-trivial superposition of energy eigenstates. This system in such a state cannot provide work reliably by point B. So there's this trade-off between work extraction and timekeeping. Here, we brought up the notion of some time eigenstate, which we can imagine is something sort of reasonable that would probably come up in the study of quantum clocks. And so there might be some sort of time observable, but you can actually prove that there does not exist any time observable. Wolfgang Pauli figured this out. We were more recently talking about Pauli in the context of Pauli's exclusion principle when looking at a quantum Szilard engine. Here's the proof. Suppose, this will be an argument by contradiction, suppose that there does exist a time observable big T. It generates a family of unitaries. So for all little t's in the real numbers, there is some unitary e to the negative I big T times little t over h bar. I'd like for you to prove for homework that the commutator of u sub t with the Hamiltonian equals little t times u sub t. Then let's notate an energy eigenstate of the Hamiltonian by E so that this eigenvalue equation is true. Also prove for homework that ut acting on E is another eigenstate of the Hamiltonian. It corresponds to an energy E minus little t. Statement 5 is true for all little t's in the real numbers. Therefore, the energy spectrum is unbounded from below. Because little t can be arbitrarily large, so E minus little t can be arbitrarily negative. This situation is unphysical. Therefore, our initial premise was false. There exists no time observable. However, we can approximate ideal time states. This is the subject of recent work. Another seeming puzzle is that if you have a clock, it's good if the clock hand moves continuously. Or in a series of steady ticks, which suggests that the clock should be in a momentum eigenstate. On the other hand, the clock hand should have a well-defined position so that it is always some particular time. Which suggests that the clock should instead be in a position I can state. So we need to combine both characteristics somehow, which is also the subject of some recent work. And in particular, if you have a system that is somewhat large, then it can have a pretty well-defined value of its momentum and a pretty well-defined value of its position. This is a reference that I personally have found useful. It has a couple of sections at the beginning that provide some background and a historical overview. That's all the material that I have for today. Does anyone have questions about what we've been discussing? Would Gaussian states be a good candidate for these clocks? One possibility is coherent states. Those have pretty well-defined values of an analog of the position and an analog of the momentum. Also, sometimes which state your clock should be in might depend on the model. I haven't thought about Gaussian states very much myself in the context of quantum clocks, and also I'm not an expert on quantum clocks, but I know that coherent states or light coherent states are one example. What were the units of the T operator? We can, those need to be time so that our T is conjugate to the Hamiltonian. And so in our unitary here, the exponential has an argument that lacks dimensions.
I think there's also a question by Soham.
Do you have your hand raised? Or are you saying it's in the chat or on YouTube?
He has his hand raised.
Okay. Would you mind unmuting him so he can ask?
Soham, are you there?
Yeah, can you hear me?
Yep.
Okay. So I'm a little confused about the three-level measure that you describe and the efficiency greater than 1. Could you just explain it once more, as in why are we getting the efficiency more than 1?
The efficiency of an engine is defined as the net work outputted divided by the heat absorbed during the step in which the engine absorbs a net positive amount of heat. So W over Q sub H. And in our engine, we have these 3 levels. Heat of that form, heat is used to bump the engine from the 2nd level to the 3rd level. So this amount of energy, E3 minus E2, is Q sub H. Meanwhile, the work is the energy outputted by the engine as it drops from the 3rd level to the 1st level. So W is E3 minus E1. And QH, as we can see from the diagram, is a smaller amount of energy. It bumps the engine over a small gap. Whereas W is a greater amount of energy. It drops the engine across a larger gap.
But the number of transitions for 2 to 3 is much larger than the transitions from 3 to 1, right? So that also
I'm afraid
needs to
there's
be
some problem with the audio.
Hello? Am I audible?
That's better.
Can you hear me?
That's better.
Yeah. So so I understand that the energies are different, and W energy from 3 to 1 is higher than the energy from 2 to 3. but the number of particles, number of transitions going from 2 to 3 is larger than the transitions, number of transitions from 3 to 1, right? So if you try to find out the total heat lost or the work gained, then 2 to 3 has more energy to it, right?
We could, I think we can possibly tune the temperatures so that the engine has basically no population on level 1 and basically all its population on level 3. And then half of that will drop down to level 1. And we can also tune the gaps if we want. I think that we can probably tune the temperatures and the gaps to make this still work out. It isn't done in that paper, as far as I know, and you can certainly do a more detailed analysis. That's my expectation. I haven't worked out those details myself, but that's my expectation, that you could tune the temperatures and the gaps to show more rigorously that this happens, but that is to be done.
So, Nicole, there's also a question from YouTube from Kispiri, which is about the efficiency of the Maser machine. We never really restore the atom to the original state, do we? So level 2 is always depopulated, it's never restored. So the efficiency calculation is incomplete.
Let me see. We end with the engine in a state in which the populations are split evenly between level 1 and level 3. Then in a refresh step, well, suppose that we started off with the engine in that state. So we could do the analysis supposing that the engine starts off in that state, then it would also end in that state. And I think in that case, we would have closed the cycle. Well, at least technically in that case, we would have closed the cycle.
Yeah, cool.
How is the clock problem in quantum field theory? There are some people who work on quantum clocks in quantum field theory. I'll actually write this at the bottom here. One of those people is Alexander Smith, recently of Dartmouth, now of St. Anselm College. So he and his collaborators and other people whose names I'm not sure of have worked on this. So I recommend looking up their papers. Another is Mohammed something, but his last name is escaping me. To get equal footing for t and x, can't we make x as parameters, which we do in QFT? One might think of doing that. The problem is just that according to quantum theory, we assign an operator to x to represent x, and we represent the time with a parameter. So if we want to accept quantum theory and say that it's a good way of describing a large portion of the world, as experiments by now have suggested, then we have to accept that, at least in this regime, that really is a good model. If you want to put the two on equal footing, then again, you can move to quantum field theory. There's another question about the quantum clock problem in quantum field theory. I recommend checking out these papers. Fabio has raised his hand. Gabriel, would you like to unmute Fabio?
Mm-hmm.
Or actually, it looks like you've posted in the chat. In the second step of the Pauli demonstration, the commutator has a big T or a little t. The commutator has a u of t with a little t as the subscript and an h. For proof on time observable, how does t act on the states? That we don't, so I'm guessing that you mean, how does the operator t act on the energy eigenstates E? That we haven't specified. At least we don't need that result for our proofs.
So there's also another question from you too, going again back to the efficiency larger than 1 question. So Frank is asking, what is the role of spontaneous emission in this issue of having the efficiency larger than 1?
My guess is that the authors assume that that is a very small probability. No, wait a minute. We're talking about lasers, and when we think about how lasers affect atoms, we take into account spontaneous emission, stimulated emission, and absorption. All 3 factors are important for understanding how atoms behave, including for understanding detailed balance. So my expectation is that when we talk about the atom's interactions with the lasers, the spontaneous emission is already implicitly incorporated into what we're saying. It's just in sort of the background theory that was worked out some years before that enables us to talk about the steps that we just talked about.
Awesome. I think there's also a couple more questions in the chat.
This was the crux of my dimensional question before. As written, the unitary has ill-defined dimensions. Yeah, maybe I'm misunderstanding the question. Oh, I see. I think I see what you mean. It's possible that, so here we have unitary. Okay, in this case, let's rephrase this. Let's say big T is just some operator, and little t, either we can say that it has no dimensions, and we normalize this argument here with just some constant to make the whole thing dimensionless, or we assign to little t the dimensions of time, and then again we normalize with just whatever constant is necessary to make the whole exponent dimensionless. So I did misspeak earlier. The thing is, whatever dimensions t has, we can always play around with. We can always play around with this constant to give the whole exponent a lack of dimensions. So just the way that, suppose that we are talking about, instead of the generator big T, the generator H, then we'll normalize what's in the exponent by H bar to ensure that the exponent lacks dimensions. So here we'll just choose whatever constant we need to in order to make the whole thing dimensionless. Okay, thanks very much for all the questions. I should head out. I'll see you guys on Friday.
Awesome. Thank you so much, Nicole. Thank you everyone for attending. And just remember, yeah, so tomorrow there are no classes, so we see each other again on Friday.
Have a good Thursday.